sometimes we have mechanistic problems that end up raising other issues that we need to talk about. So imagine this mechanistic problem where I give you this single enantiomer bromide and I ask you to predict what products it will make and to do so by figuring out the mechanism for it. And so you look at this and you see you have a secondary bromide that's stabilized by resonance. So this is probably a decent candidate for an SN1 type reaction. The solvent is certainly appropriate for an SN1 type reaction. So what you should do is start by having the bromide leave, which would then lead to an equilibrium step wherein we have a nice carbocation that's secondary, and as I mentioned, it is stabilized by resonance. So not only do you draw the initial carbocation, but you slide over that double bond so as to generate the other resonance stabilized version, which is going to be a tertiary cation and a double bond over there. Okay, so what we now have is a pair of reasonable structures, and we have some methanol floating around right up here. So what has to happen next is that the methanol must end up attacking one of these two structures. And the methanol could choose to attack from the top or the bottom in each particular case, but the methanol can attack this secondary carbocation, or the methanol could alternatively attack the tertiary carbocation. And for the sake of argument, what I'll do is just simply draw out one of those possibilities. What we're going to have now is the secondary will have a O-methyl squiggle with a cation that looks like that. And what must happen at that point is that now the methanol must come in and deprotonate according to the usual rules for SN1 and acid-base type chemistry. The outcome of this sequence of steps is that you make both enantiomers of the secondary methyl ether. So we have taken a single enantiomer and we have scrambled the stereochemistry. We have made a 50-50 mix or a racemic mixture at that position. Following through the same analysis on the other side, and it will go the same way, you make first a squiggle and then you have a deprotonation step. The final outcome is you also make the tertiary methyl ether, presumably both enantiomers, again, as a 50-50 mix. However, how do you know which one of these two dominates? And are they really different or not different
in terms of energy?
Well, the answer is that, yeah, in fact, they're different. And the easiest way to see that is that you have a tri-substituted double bond right there, which is to say you have 1, 2, 3 carbons bound to the double bond. So this is a tri-substituted double bond, which is lower in energy than a 1, 2 di-substituted double bond. This is going to be a lower energy product than this is. The product that has the lower energy double bond in it is going to be the thermodynamic product. It is going to be the more stable product. The one that has higher energy double bond in it is not necessarily going to form faster, but in this particular example, it will be the kinetic product. And so these two terms are essentially the new terms, kinetic versus thermodynamic. And really the easy one to remember, I think, is the kinetic product. That's the one that forms the fastest. The kinetic product is the one that forms fast. Speed, kinetics, speed. Thermodynamics, on the other hand, is about stability. So this is the more stable product, it is the thermodynamic product. It is possible for the thermodynamic product to also be the kinetic product. It is, however, possible for the kinetic and thermodynamic products to be different. To understand this idea of kinetics versus thermodynamics a little bit more completely, we really need to think in terms of a reaction coordinate diagram. So I'm imagining a reaction coordinate diagram for the entire process, and so the starting material starts here, but then we go to some very high energy intermediates, which is to say this carbocation, resonance stabilized carbocation, of course, which is why this process happens, but then it goes on to more stable intermediates, which is to say the protonated products, so this one and the one I haven't pictured. The more stable thermodynamic product is going to be a relatively low-lying energy level. The other product, because it has the less stable double bond, is going to be higher in energy. However, as I've indicated, it's the kinetic product. It turns out that the hump that links this energy well to that next energy well is relatively small, whereas as we're going to the thermodynamic product, we're actually going through a higher energy hump on our way down to the lower energy well. Then we go down to the final products, and it turns out that the higher energy double bond is going to remain higher in energy than the double bond of the thermodynamic product. And notice that the energy humps here are likely to be the same because because it involves a simple deprotonation step. So what matters is the fact that the activation energy to go from this intermediate down to this intermediate is lower for the kinetic process, which means that the kinetic process happens faster. However, the energies that are different in the intermediate and different in the final product, this is why the orange line is the thermodynamic product. Why this is the thermodynamic product fundamentally has to do with the double bond stability. Why this is the kinetic product fundamentally has to do with the nature of the carbocation intermediate. If you're looking at these two, which carbocation do you prefer? You prefer this one. Therefore, this resonance structure is the greater contributor versus this other resonance structure. Said another way, the resonance hybrid that I might draw will involve a greater degree of delta plus at the tertiary position and a smaller delta plus at the secondary position. Again, keep in mind that I'm talking resonance hybrid here, which means that there's some double bond character in both locations and there's some delta plus in both locations. It's just that the delta plus is larger at the tertiary position where it can handle the more delta plus. Said another way, the methanol is going to be more attracted to this end of the molecule and should attack there faster. It will be slower to attack that end of the molecule. This is why attacking the tertiary leads to the kinetic product, whereas attacking the secondary leads to the thermodynamic product. It's a higher energy hump, but if you can get there, this ends up being lower in energy overall. This is the difference between kinetics and thermodynamics. One last reaction coordinate diagram point to make here on kinetics versus thermodynamics is that if we imagine the reaction as leading to a common intermediate, which is, say, this one, we could then describe the common intermediate as having this energy and then describe what happens as you go in two different paths. So this would be the kinetic product because the difference in energy between the transition states is lower. So the kinetic product has a lower barrier to moving on to products, a lower transition state, than does the thermodynamic product. The thermodynamic product is so named because the energy wells are lower on this side. Again, what makes something the thermodynamic product is the stability of the final product relative to the other possibilities. What makes something the kinetic product is which ones form faster. So in the reaction drawn up here, you might expect to make more of this because it forms faster, unless the entire thing is under equilibrium and you wait a long time, in which case you will funnel to the more thermodynamic product eventually. And in this particular case, since every step along the way is an equilibrium step, you should be able to wait a relatively long time and end up collecting out more of the product that has the lowest energy overall, even if the other product forms faster.